So today we are cutting to the chase, if you will. We're going to be talking about the core concepts underlying the binary counting method, or I'm going to say encoding, hexadecimal, and how IPv4 addresses are actually encoded by a system. Now, the reason why we were going through the OSI model and TCP IP model in prior videos this week is because we want to show how the knowledge received from our artifacts regarding each layer can be used and applied to malware analysis. Okay, and it starts. Recall how I kind of told you that this week we're kind of giving birth, if you will, to the knowledge that will be acquired through a lifetime of cybersecurity studies. Well, this is kind of like the first base of this knowledge. Like, in order for us to hit a home run, we have to learn to hit. We have to learn the baseball stance, and we have to learn this and that. The little nuances about how to hit a base hit. Once we get that, then maybe we can start going for home runs. So now, in terms of baseball, I'm trying to teach you the underlying knowledge of how to stand in order to best address the incoming baseball. And as you can tell, I know nothing about sports. I'm just telling you about what I have observed over the years. So, anyways, we're going to talk about the core concepts of how computer systems actually understand your requests and the network protocols that are flying through the air, if you will. The first thing we need to talk about is the idea is that your computers only understand zeros and ones. So, for example, when you fire up your Python idle, for example, and you type in, print hello world, and maybe you put it inside of a for loop so you can control how many times print hello world appears on the recipient's computer screen. The one thing about Python, it is in particularly very elegant. It's really the closest thing to pseudocode. Now, when it comes to binary, what happens is that somehow, some way, everything you do, everything from requesting to go to the Amazon webpage or the Alibaba webpage, or just programming things like while loops, for loops, hello world, and all that, whatever it is, it somehow, some way gets translated into zeros and ones because, quite frankly, your computer, whether it's the original Turing computer, the scientists that cracked the code in order for us to fight, the Nazis in World War II, whether it is the Alan Turing or whether it's the latest gaming PC with the RTX 5090s and everything in between. Every piece of technology only understands zeros and ones. Okay, so when it comes to actually understanding it mathematically, each bit represents a power of 2. And in the next slide, we're going to understand that we can analyze binary, and we might as well go to the next slide, anyways, as you can see. And just so you know, this deck you see in front of you, I'm going to upload that to this week's course shell in Canvas. But anyways, we have the power of 2. So 2 to the 0 is 1. Anything to the 0 power, x to the 0 power will always be 1. So 4 to the 0 power is 1. Uh, Infinity to the power of 0 is 1. So if x to the power of 0 will be 1, x to the power of 1 will always be x. So 2 to the power of 1 is 2. 2 squared is 4. 2 to the third power, or cubed, is 8. 2 to the fourth is 16, and so on and so forth. So the purposes of only going to 8 spaces because in 8 is like the length of an octet, or 8 would be, that's, a binary, like a, shall I say, an IP address is only carried out so many times, an IPv4 address, because it is 8 bits. That IP address is 8 bits dot 8 bits dot 8 bits dot 8 bits, because it is what we call a dotted decimal point, or dotted octet, we should say. So, anyways, looking at this, binary is the power of 2, so we have our magic numbers here. The magic numbers that we develop are, because 2 to the 0 is 1, 2 to the 1 is 2, 2 to the second is 4. So as you can see, we're always doubling. So 1, 2, 4, 8, 16, 32, 64, 128. Okay, so you might ask, what is the decimal equivalent of the binary 1010? So what we do here is we can list out our slots. Our slots, we can envision these as memory slots. 1, 2, 4, 8, 16, 32, 64, 128. We can assign, what we have to do, first step is break it down into our magic numbers. 1, 2, 4, 8, 16, 32, 64, and 128. And then we assign 1010 to one of the slots, as we can see here. 10. Oh, did I get something wrong here? 1010. Okay. And so that should be 10, 10, 1, 1. So actually, I'm going to change this to a 1. What is the decimal value of 10, 11? So we have 10, 11. So what we do is we write 10, 11 here. Okay. And we say 1. Okay. 0. Oh, you know what? I made another mistake here. I'm going to change this into 0. So in other words, when we see a 1, we drop that 8 down, and you can see this should rightfully be all zeros, because the default value is always going to be 0. Okay, so I'm going to write 0, 0, and then 0, and then we'll keep everything the same. So 0, 0, 0. So we're not going to drop any of these down. The only ones we're going to drop down is when there's a 1. We can almost look at it as a way we can define, a link. So when there's a 1, it's almost like there is a link between the 8 and this. So the 8 drops down. We can look at that 1 as like a pipe. We've given an inlet for the number above it to drop down, like a slide. So we can look at the number 1 as a slide. 8 slides down. 4, because it's like this, it's blocking 4 from falling down, so 4 will remain the same. 1 second. I'm using I'm using Google Meet to catch my image, because I'm assuming that it's more compelling. It's more compelling maybe if you see my face. I don't know. I couldn't. Maybe it's because I'm ugly. Maybe you don't want to see my face. Anyways, 2, we can look at envision 1 as a slide, a fun slide. Yay! 2 slides down. As you can see, 4, that slide, it's no slide, it's a 0, so it's blocking 4, so 4 is barred from coming down. And the number 1, there's a slide here, so 1 will come down. So what we're doing is we're adding 8 plus 2 plus 1, and that is going to equal 11. Okay, so 1, 0, 1, 1 equals 11. Okay, let's try more. Let's try these, and I'll let you take the time to do these, and then we'll in the next video we'll look at the solution.